So I was scrolling through InfoSec Twitter one day and I came across this tweet about the damn vulnerable DeFi war game. So this kind of caught my eye because it reminded me of the damn vulnerable web application, where it's essentially a playground for a common web application vulnerabilities that is made intentionally vulnerable so you can learn how to exploit them. I know cryptocurrencies, DeFi, smart contracts, NFTs, that whole space is kind of generally not taken very seriously in the InfoSec community because of the scammy nature of the whole space, but people are putting money into these smart contracts and they are getting hacked for a lot of money. So not even 1 month into 2022, we have already seen a huge smart contract hack worth $80 million in the Binance Smart Chain project, Qubit Finance. And if you look at the list of hacks in the DeFi space, this website shows that you have approximately $7.1 billion has been drained from smart contracts just in the last 2 years. So scrolling down, you can see not even 2 months ago, $120 million drained from Badger DAO. So comparing these numbers to ransomware attacks, technically the amount of money being drained from the DeFi space is actually larger than the ransomware industry. So these are pretty mind-boggling numbers, and moving forward, I do feel that this is going to get worse and worse in the DeFi space because people are just putting more and more money into these smart contracts, and this space doesn't seem like it's slowing down at all. One of the factors that make smart contracts so hard to keep secure is because the code is immutable and censorship resistant. So essentially what that means is if you push out a smart contract onto the Ethereum blockchain and it has a bug in it, for example, that bug is essentially going to be there forever. And there is no way for you to actually fix that bug because of the fact that the code itself is immutable on the blockchain. So that bug is just going to be sitting in your contract until one day someone discovers it and poof, all your money is gone. I think as a penetration tester, offensive security consultant, it is an area that you should get at least a bit of understanding of. So in this video, I'm going to take you through the first challenge in the damn vulnerable DeFi called Unstoppable. This first challenge is a denial of service hack on a flash loan smart contract. The contract will provide you with loans that you have to pay back within the same transaction. So what you can do with that is once you have the funds, you can perhaps pursue some arbitrage opportunities between the different prices on different exchanges, make a profit on that, and then return all the money all within the same transaction. So the code itself in the smart contract will enforce that must happen, otherwise the transaction will revert and you wouldn't get the funds. The code for this challenge is on GitHub. You can check it out by clicking these links here. So these are the two smart contracts that we'll be looking at. The main one here being Unstoppable Lender. So this code defines a smart contract that will be performing the flash loan. To test if we've actually solved the challenge, we are supposed to write our exploit code in this function here. I'm actually completely new to Solidity and smart contract development frameworks. So this was a lot to get my head around, both understanding the Solidity code and also the smart contract development framework. So what I actually did was deployed these contracts to the Ethereum network and interacted with them that way, just to understand it a bit more, because I felt that was a much more intuitive approach for me to learn this whole thing. So I'm going to walk you through how you can deploy these smart contracts onto the Ethereum test network and try to understand what is going on and how to actually perform the denial of service attack. I actually decided to do this whole thing in the Brownie framework because it's in Python, and I am not actually too comfortable with JavaScript, which this GitHub repo is based off of. So to get started, go to this installing Brownie page and run through these commands to set it up in your machine. I have ported over the code from this first challenge into the Brownie framework on my GitHub page here, so you can clone this to get a copy of my code. I will leave a link in the description below. So go ahead and clone this repo and open it up in your favorite code editor. In this contracts folder, you'll find all the contracts from Damn Vulnerable DeFi. In the scripts folder will be the Python script to deploy those contracts onto the Ethereum network. And in the test folder is the exploit code to test if our exploit is working or not. So to deploy these contracts to the test network, you'll need to set up with a MetaMask account. So go ahead and add this plugin to your browser, and then click through these menu options to set up a new account. Alright, once you have your account set up, go ahead and click this button here and click this Show Hide Test Network and switch that on. Now we'll be able to switch to the Rinkeby test network. We can grab some test Ethereum on this network by going to this faucet page on Chainlink. Make sure you select this network as the Ethereum Rinkeby network, and go ahead and grab some test Ethereum for your account. We are actually going to need 3 accounts to set up this first challenge, so click this button to create a second account and grab some Ethereum in that as well. And then for a third. And once these transactions confirm on the network, you'll be able to see in your account you've got 0.1 Ethereum on each account. Next, we will import our accounts into this project. Create a file called .env. And in this file, we are going to import our private keys of the accounts that we just set up. So in MetaMask, go ahead and click this button here and click on Account Details and export account private key. Obviously, I'm only showing my private key in this video here because this is just a test network. A final thing we need to set up in our project is this Web3 Infura project ID. This is essentially going to be our Web3 API endpoint where we're going to be deploying our contracts to. To generate an API endpoint, register an account on infura.io. Essentially, we can either download the whole Ethereum blockchain and then publish our contract that way, or we can use the API endpoint provided by Infura just to avoid downloading the whole blockchain. Once you're logged in, click this Connect to Ethereum network and select Ethereum and just give it a name. And then copy this project ID value here and put it into our environment variable. Alright, now that it's all set up, we can finally start to deploy the contracts and start looking at the code in more detail. So the first contract that we're going to deploy is this damn valuable token contract. It's just got a constructor which essentially mints damn valuable tokens to whoever that deploys this contract. Type in Brownie console network rinkeby. So hit enter and then we'll drop into a Brownie Python shell. Made a typo there, just try that again. So the first thing we're going to do is import those private keys that we have set up in the environment variables. Essentially, this is pulling from this Brownie config file here, where we are defining wallets attacker as private key attacker in our environment variable. Next, we'll pull in the deployer and some user address as well. Now that we've got our 3 accounts imported, let's assign them to variables. Okay, now that we have our account set up, we can go ahead and deploy the first contract, which is going to be that damn valuable token contract. To do that, we go token equals damn valuable token dot deploy from the deployer. So the transaction just got sent and the token contract was deployed at this address. We can actually see this address on Etherscan. If we go to rinkeby testnet explorer on Etherscan, we can actually see this contract on the blockchain. So there it is there. It was created 1 minute ago from this address and it just created this new contract. So if we click this contract, we can see that this contract has actually created a new token called DVT. And on this token tracker, we can actually see the holders of this token. At the moment, all the tokens belong to our deployer address, which was minted upon creation of this smart contract. In the contract that we just deployed, we can actually see the functions that this contract has. So you can read the contract information there and also write to the contract. If you remember in the code, our damn valuable token only had that constructor. So all of these functions are actually inherited from the ERC20 standard. So what we can do now is we can read from the contract. So for example, we can query this for the balance. So if we copy our account 2, we can check the balance of that account, which is the max amount there. We can check the decimals of this token, the name, the symbol, and the total supply. So these functions in the read contract section doesn't actually cost any Ethereum to execute because they are essentially just reading information off of the blockchain. In the write contract section, these will actually cost Ethereum to run because with these functions, we will be actually making changes to the state of the Ethereum virtual machine. You can actually interact with this contract now directly from MetaMask. If you click this connect to Web3 button and connect these accounts with MetaMask. So now that is connected, we can actually interact with the smart contract. So for example, if we want to make a transfer to a different account, we can copy the address. So for example, let's transfer some DVT tokens to account number 1. So switch over to account 1, copy that address, and let's transfer 100 tokens to that address. And don't forget to take the X0 off from the start of the address. A MetaMask pop-up will appear, and click this confirm button to transfer the DVT tokens. And we can view our transactions by clicking this button here. Once that transaction has confirmed, we can go into MetaMask and confirm we actually received those 100 tokens in account 1. There it is, the token has appeared. So we can either interact with the contract through the GUI here, or we can actually do the same through the Brownie terminal as well. Let's give some tokens to our other accounts. And transfer some tokens to the attacker address as well. And after those transactions have confirmed, if we refresh this, we can see all 3 accounts have a bit of DVT in them now. So I hope that made sense. If you're not too familiar with Ethereum and how it works, I would encourage you to play around with these functions here and the terminal to interact with them a bit more before moving on to the next section. Okay, now we can finally start to deploy our actual smart contracts that has the vulnerability in it. So we're going to deploy this unstoppable lender contract. To deploy this, it will need an address, which is the token address that we just deployed. So we're going to go pool equals unstoppable lender dot deploy, give it the token address, Alright, now our lender contract has been deployed at this address. So this contract just has 2 functions, one deposit tokens and one for executing the actual flash loan. So this deposit tokens function is a way for this contract to keep track of the pool balance locally. So you can see there is this pool balance variable here where once a deposit is made into this contract, it's going to add to the pool balance. So let's set it up and transfer some tokens into this smart contract. So first we have to approve of the transfer from the sender. We do that by calling the token.approve function, give it the pool address, and send it from the deployer account. And now we can actually call this deposit tokens function in the pool to transfer the funds into the smart contract. You can check the pool balance by going pool.pool balance. That looks correct. And going back to Etherscan, if we refresh this page that keeps track of how many tokens each account has, you can see now we have 4 holders, 3 addresses, and 1 contract. Now to execute the flash loan, we actually have to interact with this contract from a receiver unstoppable contract. So from here, we execute the flash loan, which calls flash loan in the pool contract. It goes through here and it calls back to the receiver tokens in the receiver contract. This can be deployed from any user, so we will use our third account called some user. To test if this is all working, we will call the execute flash loan on the receive contract from this other user and see if we can get a loan and repay it back within the same transaction. Let's have a look at what is happening with this transaction on Etherscan. From here, we can see that a transaction was made from the contract address to our some user address, and then the some user address transferred the money back to the contract address, all within the same transaction. So here our some user address account, we can see 10 tokens came in and then 10 tokens went out. So at this time, the flash loan is working as intended and everything is good. So now we finally get to the part of the exploit. For this challenge, our goal is to interact with this contract in some way to make it not be able to execute the flash loan anymore. Essentially a denial of service attack. To do that, we'll have to look at the code for unstoppable lender. Essentially, there are 4 places where in this flash loan contract it could fail. So these are the require statements and the assert statements. We need to have a look at each of these locations where it's possible for an attacker to permanently make one of the statements fail. So for this first one, borrow amount equals 0, you must borrow at least 1 token. That is the borrow amount that we pass into this flash loan. So even if this fails, it's not going to be anything permanent. The second check is here where the borrow amount has to be less than the actual balance that is in the contract. Again, there's not much we can do here. What we're looking for is something that can permanently alter the state so that it's no longer possible to execute flash loans. So this assert statement is where this bug occurs. This is checking if pool balance equals balance before. Balance before is calculated by calling this a balance of function on the damn valuable token itself. And this pool balance is a local variable. So potentially if one of these values can be either increased or decreased to make it not be in sync anymore, then essentially this flash loan will never be able to fully execute anymore because it'll fail this assert statement. So if we open up Etherscan again, we'll put in our contract address in here to check what is the balance of that account. Currently it has 1 million tokens, so that looks correct. And if we go to the contract itself, the local variable is here, which is pool balance, which at the moment they are equal. So in our hypothetical scenario, the developer of this smart contract assumed that it was only possible to deposit tokens into this contract by calling this deposit tokens function here, which will then update the pool balance. But actually there is a different way we can transfer DVT tokens to this contract without calling this deposit tokens function. That way the balance before will be increased while pool balance remains the same, which will make these two out of sync. And the way we can do that is through our original DVT contract. So click over to the right contract button over here. And you may recall that we previously transferred some funds to our attacker address with this transfer function. So this transfer function is actually in the ERC token itself. So if we transfer some funds into our smart contract address using the ERC token transfer method, this will update the balance before value, but the pool balance will remain the same. So we can do that by specifying the pool address here, and we'll just transfer 1 token. You can either click this button to initiate the transfer from MetaMask or do it through the terminal. Through the terminal, it would be token.transfer to the pool address, 1 token from the attacker. Alright, now that transaction has confirmed, we can go back to the pool balance and query that again, and that is still 1 million tokens. But if we go to the token and execute balance of, you can see actually this has 1,000,001 tokens in there. So looking back at our code, this pool balance variable will be 1,000,000, this will be 1,000,001. So this assert statement will never be true, which means this flash loan functionality has been disabled essentially. So we can confirm that by trying to execute the flash loan again, and this time it'll fail because of that assert. So essentially now we have solved the challenge. If you thought that was a lot of work setting this whole thing up, it definitely is, but I only showed it this way in the video because as someone who is learning this for the first time, I felt it a bit more intuitive to load it up into Etherscan, doing it through MetaMask, which I felt helped me internalize what was going on a bit better. To automate this whole process, you can actually run this a test.py, which will do exactly what we have done through this video, but it'll do it automatically and it will deploy the contracts into your local blockchain, so the transactions will go through much quicker. So to run through the test, all you need to do is Brownie test unstoppable. If we run this test without inputting anything in this exploit section, the test will fail with this warning here. And if we put in our exploit, which is token.transfer pool, transfer 1 token from attacker. And rerun that test. Now we have passed and we have solved the first challenge. So that's it for the first challenge of Damn Vulnerable DeFi. I am pretty new in all this, so hopefully I didn't make too much mistakes in this video and it all made sense. Alright, give this video a thumbs up if you would like to see more content like this, and thanks for watching. I will see you in the next one.